This time around in the force unit, it's time to look at net force. Now, net force is basically talking about an unbalanced force. Now, I say unbalanced force because it's the sum of all the forces acting on an object. And it really doesn't have to be unbalanced, but that's one type of it, is there is an unbalanced force and a balanced force. If it's unbalanced, it's moving. So unbalanced equals moving. So unbalanced, moving. And a balanced force means not moving. And this all goes back to Newton's first law. Remember, a object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. Well, that unbalance would mean that it would start the object that stopped moving, or it would stop the object that is moving. A balanced force means it's not moving at all, and nothing's going to change about that, because all the forces equal each other out. So a net force is really just the sum of all the forces, meaning we add together all the forces. Remember, forces are a vector, so that means some might be going to the left and some going to the right, which means they'll cancel each other out, or they'll at least neutralize each other a small bit, and we'll take a look at that. So here we are. Here's an unbalanced force. We have this lovely couple here doing a tug of war with this lovely couple. If this couple, both together, manage to pull the rope 500 newtons to the left, and this group only managed to pull it 450 newtons to the right, it's unbalanced because one force is greater than the other. What we can do then is add those two together, and we'll get the sum of those forces, or the net force. And what we would do is we would add those together, and we would figure out the net force is a net force of 50 newtons to the left. So I'm going to make it negative. And that's what I would have done over here. I just designate that as negative, and then I do negative 500 newtons plus 450 positive newtons is equal to negative 50 newtons for the net force, and it's unbalanced because you get a force in a certain direction. That being said, let's take a look at this one. With this one, you have a box, and this is a free body diagram where the box is represented with a box, but it is also our point that we were talking about before. And you have 5 newtons to the left, 5 newtons to the right. Well, I'm going to go ahead and make that one to the left negative, all right? Now, if I have 5 newtons plus a negative 5 newtons, then I'm going to get a net force of 0 newtons, right? So that means my net force in that case is balanced out to 0. And that's what a balanced net force means, is you end up with 0 total net force, okay? Okay, so let's take a look at a couple of these problems one at a time to see how a net force would play out. Okay, so let's take a look at one of these problems. Person A pushes with 50 newtons of force to the right on a large 10 kilogram box that person B is pushing with 40 newtons of force to the left. What is the net force and acceleration in the box? So we have everything we need to do this problem. And first thing I'm going to start to do is draw a free body diagram. I have my box right here. And so let's go ahead and add something into it. We already said that it was a 10 kilogram box. So we know that, 10 kilograms, okay? And then we have person A and person B, and we know that they can push in different ways. One's pushing to the right, and one is pushing to the left. Now, we need to label what each of those is. So this first one to the right is 50 newtons of force. So I'm going to put 50 newtons, put a little slash in my O so we know that it's 50. And then the person pushing to the left is 40 newtons. A little slash there, newtons. It's a terrible one, I'll write that again. Okay, so now we have everything that we need to visually see what's going on, but we need to figure out what's going on. And so to do that, the net force is just going to be equal to all the forces added together. right? And so we have the force of A plus the force of B. And I'm going to go ahead and label this one force A and this one force B, because you just get to label them what they want to be. Now I will say that since this one is going to the left, we're going to make it a negative value, okay? And so then we can plug in what we just figured out, which was the net force is going to be equal to 50 newtons plus a negative 40 newtons. And we can figure out that the net force is equal to 10 newtons, and it's positive, so it's to the right. So you could even write to the right if you wanted to. But the positive should do it as long as you've designated that for that. So that solves this part. What is the net force? Well, we have that right here. The net force is 10 newtons to the right. The other part seems tricky. Acceleration. What is the acceleration of the box? But it's not that bad. For acceleration of the box, I'm just going to use F is equal to m times a, meaning force is equal to mass times acceleration. But I'm going to solve it for acceleration. And remember, we can put this in a triangle, if that helps you, mass and acceleration right there. And so now I can rewrite this as acceleration is equal to force divided by mass. Well, that force is the net force acting on the box, which we figured out was 10 newtons to the right, and the mass we know is 10 kilograms. So 10 divided by 10 is 1, and that's going to be an acceleration, which is meters per second squared. So we can say to the right, it's accelerating at 1 meter per second squared. Now the second one can look fairly simplistic, but you have to remember something. So it says that a rope pulls a 50 kilogram bucket, that's this, straight up with a 490 Newton force. What is the net force and acceleration? Well, it says net force because this isn't the only force acting on it. We assume this bucket is on Earth. If we know that it's 50 kilograms, we have another force acting on it. That force is going to be acting straight down though, and that force is going to be the force of gravity. Okay? Now, I already pointed out over here that this was an applied force because we're pulling on it here. The force of gravity is simple enough to figure out, is just mass times little g. And remember, little g is equal to 9.8 meters per second squared. And so we have everything we need to calculate this, which is now going to be 50 kilograms times negative 9.8 meters per second squared. I made a negative because it's going down, and that's usually done that way. So now we can say that this force of gravity is equal to, would you look at that, 490 newtons, but down. So I can now say very quickly what my net force and acceleration is. So since it's being pulled up by the exact same amount that it's being pulled down, then its net force is 0 because 490 plus a negative 490 is 0. And if it has 0 net force acting on it, it has 0 acceleration. So I could write both of those very quickly. Force net equal to 0 newtons. Acceleration is equal to 0 meters per second squared. And I'll box in my answer. The third problem states a 500 Newton force is applied to the right of a 10 kilogram box that is then accelerated at 20 meters per second squared. What is the force of friction on the box? Well, you just have to start from a different place. I drew my free body diagram, and I drew the applied force, the overall acceleration, the mass of the box, and then I realized that frictional force always opposes motion, and so it has to be going in the opposite direction. Then I realized that F equals ma is really the net force is equal to the mass times acceleration. And so our net force is going to be equal to 10 kilograms, that's our total mass, times our total acceleration, which is 20 meters per second squared. So it has a net force of 200 newtons being applied to the right? Now I can use my other formula for net force, where I just add up the components and I rearrange it to solve for the missing force. In this case, the frictional force. Notice it's of a K because it's moving, so it's a kinetic force. And so I just subtract FA from both sides, force applied from both sides, and I get that frictional force will be equal to the net force minus the applied force. And so I can put all of that in pretty easily, that it's just 200 newtons minus 500 newtons. And yes, that is going to give me a negative number, but that should work if I have that frictional force going to the left, and it should be negative. So it's going to give me a negative 300 newtons, and that's going to be my answer. So here I've worked out number 4. A 400 Newton force is applied to the left of a 10 kilogram box that is then accelerated at 35 meters per second squared. What is the force of friction and direction acting on the box? Well, you can draw out most of this with your free body diagram. They said it was to the left, so I made it negative 400 and negative 35. I used my net force equals MA to figure out the total force acting on it, and I got a negative 350 newtons. And then I use my other net force formula, where you just add up all the forces working on it, solved it for the force of friction, kinetic friction, and I said the net force minus the applied force, put in my values. Notice I have a minus a negative, which is a positive, so this is negative 350 plus 400 newtons, and that gives me a positive 50 newtons, and I know that positive is to the right, so I say 50 newtons to right. There it is. Now this last one is all conceptual, but let's take a look at it. A 1,000 Newton force is applied to the left of a box, but it does not move. What do we know about the static friction acting on the box? So I put it on the wrong side, but I went ahead and drew it out, and it's okay as long as I make friction go in the opposite direction. But I put that 1,000 Newton force, and then I have this frictional force, static friction, in the opposite direction. Now, I probably could use one more saying that it did not move, right? So there is no acceleration, but I might just write that. So no, don't need an equal, acceleration, right? So because of that, that means that force isn't enough to move it, meaning that it has to be a balanced force, that this static friction has to be equal to this 1,000 Newton magnitude. That's the only reason it wouldn't move, because it is a balanced force. So what do we know about the static friction acting on the box? That it is equal to the amount of applied force, because it's not moving, it's not accelerating. And that's the final problem.